The whole point of graphical models is to express the conditional independence properties of a probability distribution. And the D-separation criterion gives you a way to read off those conditional independence properties from the graphical model for a probability distribution. So in the last couple videos, we looked at these three sort of special little cases involving three random variables, A, B, and C. And we looked at the case where we had C, so we had A and B conditionally independent given C. We had this tail to tail, so we had tail to tail type of relationship. And then we had another one where we had, I guess we had A going to C going to B, and this was a head to tail or tail to head type of relationship. And we had a third one which was A and B both going to C. And this was a head to head relationship. Head to head. So they met head to head at C, head to tail at C, and tail to tail at C. And in all of them we were thinking about what happened when we conditioned on C. And in these we found that A and B were conditionally independent given C, and this one A and B were conditionally independent C given C, and in this one they were marginally independent. So the D-separation property, or the D-separation criterion, is a vast generalization of these. So in order to introduce it, we're going to need a little bit of terminology and a couple definitions. So first, just a standard sort of graph theory term is the descendants. The descendants of a vertex in a graph. So let's draw a line here. So this is something different. The descendants of a graph, or rather of a vertex in a graph, are just all those vertices that can be reached. So if I have some graph like this, something like this, and this is descendants in a directed graph, and usually in a DAG, in a directed acyclic graph, we think about the descendants. The descendants, the descendants of this node here would be all the ones below it in some sense, all the ones which can be reached from that. So these would be the descendants. They're all the nodes, all the vertices that can be reached from this vertex by going in the direction of the arrows, by following edges in the direction in which they are pointing. So all the descendants of this node would be this one, and this one, and so forth. So that's what the descendants of a node are. And now we will introduce a critical little definition. Well, before I state the definition, let's do the setup. So now, before we were talking about A, B, and C being random variables, and now we're going to generalize our perspective a little bit, and we're going to think about A, B, and C being sets of random variables. They could have been sets of random variables here. They could have been vectors of random variables. But we're going to explicitly now think of A, B, and C as subsets. So A, B, and, well, maybe before I say that, let's say let G be a DAG, a directed acyclic graph, and let A, B, and C be disjoint subsets of vertices of G. So, we're sort of conflating vertices and random variables, since we have this sort of one-to-one correspondence for the graphical model. There's this sort of one-to-one correspondence between vertices. Well, between vertices and random variables. So by thinking here, we're thinking of A, B, and C as subsets of vertices, and of course for each vertex there is some random variable. And of course a vertex could also be a vector of random variables. Okay, so we have these subsets of vertices. So for example, maybe just to give you an example, let's see. So A could be in this little graph. A could be, say those two. So that could be A. And then B might be like this guy. And C might be, I don't know, if we draw C in green, C might be this guy. And this one might not be represented at all in A, B, and C. So they're just disjoint subsets, but they're not necessarily the whole graph, right? So I didn't say that the union of all of them was all of the vertices. I just said that these were disjoint subsets of vertices. Okay, so this is our sort of little setup. Maybe let me make that explicit. So A union B union C is not necessarily all of the vertices of G. Okay, and now we have a definition which will be essential to D-separation. A path, and okay, so what is a path? I haven't really said what a path is. A path is a sequence, so a path from this vertex to this vertex is a sequence of edges for which it's a sequence of edges that is connected in the sense that it's one edge. So the graph, the sort of induced graph on that set of edges is connected, and actually that's a better way to say it. So here's a better way to say it. So a path is a sequence of vertices for which there is an edge in the graph for each successive vertex in the sequence, for each pair of successive vertices in the sequence. So like if this was vertex 1, 2, 3, 4, 5, then there's an edge from 1 to so the sequence of vertices will be 1, 2, 3, 4, 1, 2, 3, 4, and there's an edge between 1 and 2, it not necessarily going in this direction. There's an edge between 2 and 3, and there's an edge between 3 and 4. So another path would be 1, 2, 5, because 1 to 2 has an edge and 2 to 5 has an edge. But what would not be a path? So 1, 3, 4 would not be a path because there's no edge between 1 and 3. So I think that's probably clear. It's a path. And note, since 1, 2, 5, for example, is a path, we're allowing for these paths to be not necessarily directed. We're in the sense that we're not necessarily going in the direction of the edges along this path. Okay, so with that clear, a path, so we say that a path between two vertices in this graph G, so we fix this graph G, and we say that a path between two vertices is blocked if it passes through, and maybe I should say blocked with respect to C. So we fixed G, our graph, and we have these three subsets, A, B, and C, and a path between two vertices is blocked with respect to C if it passes through a vertex, well, let's call it V, such that either one of the two properties holds. Either A, the arrows or edges, the edges are head to tail or tail to tail, and V, that vertex that it's passing through, is in this set C, or, so we say that a path is blocked if it satisfies one of these two properties, if it passes through a vertex such that either A or B, the arrows are head to head, and V, this vertex that it's passing through, is not in C, and none of its descendants are in C. None of the descendants of V in this graph G are in C. So let's think about, so maybe take a moment to get your head wrapped around that. So for example, so let's think about this little graph here. A path, not necessarily directed, between two vertices is blocked. So here, let's see, I just made this up on the fly, but let's see what happens here. So C, you should think of C as the set that we're conditioning on. That's what's going to happen. And here, the path 1, 2, 3, 4, that was this path. This path is blocked because it passes through vertex 2. Vertex 2 is in C, and the relationship between those arrows, the arrow from 1 to 2 and 2 to 3, is a head-to-tail relationship. So it's head to tail. So that's blocked. And the other one, let's see. So here, this is actually a good example. So B. So let's look at the path from. So this is perfect. The path 1, 2, 5. 1, 2, 5. So the path 1, 2, 5 starts from 1, goes to 2, goes to 5. And in this case, this is also, well, wait, is it blocked? Oh, no. So this is not blocked because, well, the only vertex on the path for which there's any one of these relationships, head, tail, 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 or head, head, is 2. That's the only intermediate vertex on the path. And let's see. So it's in C, but this is not a head-to-tail or tail-to-tail relationship. This is a head-to-head relationship because we go 1 to 2, and we have a head at 2, and we go 2 to 5, and that's pointing, so the arrow goes from 5 to 2. So this is a head-to-head relationship with respect to that path. So that path is not blocked. Well, I guess we should check the other one. Well, for B to be satisfied, V would have to not be in C, but it is in C. So B is clearly not satisfied. So that means that neither of these, neither A or B, is satisfied, and so the path 1, 2, 5 is not blocked. So that was just a simple example, and we'll do some more detailed examples of this in the future. And now I need to give you, well, I'm almost out of time for this video. Let me stop there, and we'll finish up. We'll give the formal definition of D-separation and the theorem. We'll state the theorem briefly in another video, and then we'll look at some examples. We'll work out some examples of how to apply it. Okay, see you soon.